Hi everyone, greeting of the day. In the last session, we have discussed about the topic which is related to the IIR, which is nothing but infinite impulse response, where we have seen the introduction of IIR, and after that we have studied the design of our design the structure of IIR filter using some techniques, nothing but direct form 1, direct form 2, parallel form, and cascade form. Followed by at the end of that session, we have seen the difference between FIR and IIR, where in that difference we came to know that the difference of converting the analog signal to digital, that means analog filter to digital filter, will be simple. That means it is directly can be converted from analog to digital when we come to FIR filter, where when we discuss about the IIR filter, where first that analog filter, that means the signal will be converted into analog form, then after that it will be reconverted into the digital form. So that is the main difference we have seen between the IIR and FIR. So based on the particular point, let me discuss how that analog transformation will be happen first, then after transforming that into the analog form, how it is converted into the digital form, we will see in this session. So for that, we are going to study two techniques, which is nothing but Butterworth filter and Chebyshev filter. So for that particular point, how the conversion is going to take place from analog, for the first transformation of analog, then after transforming that into the analog, then it will be converted into the digital with the help of the techniques nothing but Butterworth filter and Chebyshev filter. So in this session, let me discuss first with a topic which is nothing but Butterworth filter. So coming to the contents which we are going to discuss today, just a small introduction related to the Butterworth filter, followed by what are the steps we are going to design analog low pass Butterworth filter. That means what are the steps involved for designing the analog low pass Butterworth filter. So based on particular steps, let me have two problems how that analog form designing of analog low pass Butterworth filter is going to take place. Let's start with the introduction of this Butterworth filter. Here, as usual, in the last session we have discussed, so the popular method of designing IR digital filter involve the design of equivalent analog filter and then converting that analog filter to digital filter. So we just now I told you first what we are going to do, we are going to design the equivalent. So just now we have discussed first the thing what we are going to do, first we are going to design. First step is designing of the equivalent analog filter. So in this particular IIR filter, the main thing is that we are not directly converting the analog filter into digital. First what we are going to do, we are designing the analog filter, and then after designing this particular analog filter, then it will be converted into the digital filter. This is the main difference between the IIR and FIR. Now for that, what are the techniques involved? So in this today's session, we are discussing about a Butterworth IIR filter. So how to design a Butterworth IIR digital filter? First what we are doing, we are analog Butterworth filter transfer function is determined. So first what we are going to do, we are designing the equivalent analog filter. For that, first an analog Butterworth transfer function. This is the main thing. First what we are going to do, we are designing the Butterworth IIR digital filter. That is, first in that first step we are going to design the Butterworth filter, which is nothing but the transfer function with the given specifications. So when we take some problem where we will give some different types of specification, with the help of that specification, first we are designing the Butterworth filter, that is nothing but the transfer function, analog Butterworth filter transfer function we will design. Then that analog transfer function is converted into the digital filter. So for this conversion, so how this will be converted from analog Butterworth transfer function to digital filter means, here we will have two more type of techniques. One is nothing but impulse invariant transformation or bilinear transformation. Please keep it in mind, we will discuss these two topics in the upcoming sessions. So here our agenda is, first we are going to design the equivalent, this is the first thing, we are going to design the equivalent analog filter. After designing the equivalent analog filter with the help of the transfer function, then after getting this transfer function, what we are going to do, we are now converting into the digital. This is the second step. Okay, so we are not directly converting analog to digital. First what we are doing, we are designing the analog filter with the help of transfer function. after deriving the transfer function, analog filter transfer function, that formed transfer function is converted into the digital filter. So here in this second step, what are the techniques we are using to design or converting that analog transfer function into digital filter means, this is the first one, that is impulse invariant transformation, and this is the second thing, which is nothing but bilinear transformation. With the help of these two techniques, we are converting that analog transfer function into the digital filter. I think you have got a clear point. The main difference between IIR and FIR is, in the FIR filter, we will directly convert the analog filter into digital filter. But here what we are going to do in the IIR filter, first we have to design the analog filter with the help of transfer function. That is, we are going to design the transfer function of the analog filter. After designing the transfer function of the analog filter, next step we are going to convert that into the digital filter. So for this purpose, for designing this particular analog filter with the transfer function, here we are using two techniques. One is Butterworth filter and second one is Chebyshev filter. So after that, getting this transfer function of the analog filter, then in the second step, by using the impulse invariant transformation and bilinear transformation, we are going to convert that analog into digital form. This is the main difference between the analog FIR and IIR filter. So here you can see a small thing. The filter passes what? The Butterworth filter, IIR filter passes all the frequencies which is below omega c. So which passes the frequencies below omega c, that frequencies we are going to call, that region we are going to call it as a passband of the filter, and which blocks all the frequencies which is above. That means it only passes the frequencies which is below cutoff frequencies. That reason, that passing of the below frequencies omega c, that is said to be a passband of that filter, and it blocks all the above frequencies which is greater than omega c. So that reason we are going to call it as a stop band. So where what is omega c? Omega c is nothing but one cutoff frequencies. So or else we can call it as a critical frequency. The critical frequency, it processes all frequencies which passes all the frequencies through omega c. So that reason is said to be a passband reason, and if it blocks the frequencies, that type of reason we are going to call it as a stop band filters. So based on this particular 2 points, let's we have a magnitude response. So what is the magnitude function of the Butterworth filter? Just keep it in mind. The magnitude function of the Butterworth filter is given by mod j omega is equal to 1 by square root of 1 plus omega by omega c whole to the power of 2n. So where n is equal to 1, 2, 3. So this is the equation which is related to the magnetic function of the Butterworth filter. So what is n here? N is nothing but the order of that filter. Whether that order may be a 1, 2, 3, 4 and so on. So that is nothing but order of the filter, and omega c is nothing but the cutoff frequency. So based on this particular, if we draw that magnitude response of this Butterworth filter, this is the thing. So if we observe the diagram, the response is monotonically reducing. See here, as the order of the filter is going to increase, automatically the response is going to monotonically reducing. So characteristics is close to the ideal response when the order is increasing. So for example, see here, this one n is equal to 2. Now second one n is equal to 3. If we see here, n is equal to 2, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5. As I am going to go on increasing the order of the filter, it forms characteristics are going closer to the ideal. Okay, characteristics is going to the ideal frequencies, all ideal responses. So this is a small graph which shows the characteristics of the magnitude response for the low pass Butterworth filter. So here, as usual, just we have seen the 2 points. Omega c is the cutoff frequency. This is the main cutoff frequencies. When it passes all the frequencies, so this reason we are going to call it as a passband reason or passband edge frequencies. It blocks the frequencies which is more than omega c. So this reason we are going to call it as a stop band or stop band edge frequencies. So you can see the small structure or graph which is related to the magnitude response and frequencies. So we got passband attenuation. This is the passband attenuation. It is given by 1 by square root of 1 plus omega square, and AS is nothing but the stop band attenuation, that is 1 by square root of 1 plus delta square. here omega p is nothing but the passband frequency, omega s is nothing but the stop band frequency, and omega c is nothing but the cutoff frequency. So here this total is nothing but the frequency response, magnitude frequency response of the Butterworth filter. So this is the small introduction which is related to the Butterworth filter. So based on all these characteristics of Butterworth filter, let me see how this analog low pass Butterworth filter is going to design. So let me say have a small steps, that means 1 to 5 steps where how this design happens, that means how this analog low pass Butterworth filter is going to design. So in this first step, from the specifications, find the order of the filter n. First point, in the first step we are going to find the order of the filter. So for that, what happens in the given problem, if any problem is given, in that we will have some different types of parameters or specifications will be given. So with the help of that specification, the specifications is nothing but this one. So it may be a passband attenuation, that is AS, AP, omega S, omega P, or lambda or epsilon. Okay, based on this particular specifications, we are going to finding the order of the filter capital N. So for this, we are two formulas. One is, if the specifications is given, that is only AS, AP, omega S and omega P. So if these are the specifications given, then we need to use this particular formula, that is n greater than or equal to log under square root 10 to the power of 0.1 AS minus 1 divided by 10 to the power of 0.1 AP minus 1 whole divided by log omega S by omega P. When we are going to use this particular formula, when only these specifications are given. So depending upon the specifications, we are going to use either this formula or this formula. So two formulas which is used to find the order of the filter. Okay. Now, if they have given the lambda or epsilon, so for lambda is equal to square root of 10 to the power of 0.1 AS minus 1, or for epsilon it is square root of 10 to the power of 0.1 AP minus 1. So if these specifications are given, we need to use this formula. Okay. Be careful. First, while you get a problem, just observe the specification. So depending upon the specification, either you need to use this formula or this formula. Okay. So after getting the value of the order n, the second step, what we are going to do? So here in the second step, round off to the next higher integer. For example, if I get n is greater than or is equal to 1.7. In the first step, if I get the value of n is equal to n greater than or equal to 1 by 7, so here in the second step, what we are going to do? We are rounding this value to the next higher value, that is n is greater than or equal to 2. Okay, n is greater than or equal to 2. That means whatever the value we are going to get, we need to round up that value to the nearest higher integers. If it is 1.2, then we need to round off to 1. If it is 1.7, we need to round off to 2. If it is 3.7, we need to round off to 4. Like this, we are going to round off to the next higher integer. So that is the second step. In the third step, after getting this value, for example, we got n is equal to 2, greater than or equal to 2, then we are getting the transfer function as omega c by capital N. Here the omega c is equal to 1 radians per second, and I got here n is equal to capital 2. Clear? So third step, you are going to find out the transfer function of h of s. For that, omega c is equal to 1 radians per second for the value of capital N. Now I got omega c is equal to 1. And for the capital value of the n, what I got here in the second step, I got to 2, for example. Now, how I am going to form the transfer function means, please be careful, you need to by heart this particular tabular column where n and its factor. If n is equal to 1, the factor will be s plus 1. If n is equal to 2, the factor is s square plus square root of 2s plus 1. According to the values what I am going to get in the second step, we have to take that particular factor. For example, I got here n is equal to 2. Now, I will write the transfer function 1 divided by, if the value is n is equal to 2, what is the factor for value that n is equal to 2? S square plus square root 2s plus 1. So, I am writing here s square plus square root 2s plus 1. Now, here the transfer function is formed. So, I think you got a clarity how we are going to form the transfer function here. That is, if to find out the value, for finding the transfer function of h of s under omega c is equal to 1, depending upon the value of n is equal to 2, I got here 1 by 2. So the value of 2, the factors of the 2 is s square plus square root 2s plus 1. So based on that particular, here the transfer function h of s is equal to 1 divided by s square plus square root 2s plus 1. Here in the third step, we found the transfer function. Fine. Now, after getting the transfer function, in the fourth step, we need to calculate the value of omega c, cutoff frequency. So for that, here also please keep it in mind, depending upon the specifications, if the value what you are going to get, if it is omega p, just take this, or if it is omega s, just take this. Okay. Why? Because already you will have ap, as, and you know the value of capital N. Just you need to find, search in the question whether they have given the passband frequency or stop band frequency. If they have given the passband frequency, just use this one. Or else if they give the stop band frequency, just use this one. Depending upon the specifications given in the question, just take this particular formulas, either omega p or omega s. So after calculating the value of omega c, so based on this particular, we will get the value of omega c. So after getting the omega c, now here we are going to find out the new transfer function, where in third we got h of s. In the third step we got h of s. After that omega c is there. So after getting the value of omega c, what I am going to get? Finally I am going to get the new transfer function ha of s is equal to, when I substitute s tends to s by omega c. So in all the values of s, if you see here, for example, we got this one in the third step. In the place of s, I am substituting s by omega c. Okay, by substituting s divided by omega c in the third step, I am going to get the new transfer function ha of s. This is the main transfer function of the analog low pass Butterworth filter. Okay, and finally this is the conversion. That means what we have designed here, just we have designed the transfer function of low pass, analog low pass Butterworth filter. So that is nothing but ha of s. Okay, clear? Now just we will recall, in the first step we are finding the value of capital N. In the second step, after getting the value of capital N, we are rounding that value to the next higher value. In the third step, we are going to find out the transfer function of the Butterworth filter based on the value what we are going to get in the second step. In the fourth step, we are going to find the value of omega c, and finally, depending upon fifth one, ha of s is the new transfer function of analog low pass Butterworth filter by substituting s tends to s divided by omega c. So these are the 5 steps which we use to design analog low pass Butterworth filter. So very simple. Just what you need to means, you need to keep all the formulas in mind while you are designing this particular low pass Butterworth filter. So based on this, just we will take one formula, one problem. How the specifications will be given. Design an analog Butterworth filter. Just observe, we are just designing the analog Butterworth filter. So which has a -2 dB passband attenuation at a frequency of 20 radians per second, and at least -10 decibels stop band attenuation at 30 radians per second. So what are the specifications they have given? 2 decibels is nothing but what is passband. So we got alpha p, stop band we got alpha s, 10 decibels, and what is 20 radians per second? It is at passband attenuation, that is omega p, and stop band attenuation we got omega s is equal to 30 radians per seconds. So based on these particular specifications, what alpha a, alpha p, alpha s, omega p, omega p, omega s. So based on this particular specification, which formula I need to find out? I need to consider this formula. I told you in the first step we got 2 formulas, specifications which is related to alpha s, alpha p, omega s, omega p, another one which is related to lambda and epsilon. Now I consider this particular thing, and also I got all the values. Now after substituting all the values of this passband attenuation and passband frequencies, stop band and stop band attenuation and frequencies, what the value I am going to get here? Just I have substituted the values here, 10, 1. So after calculating this, I got 3.37. So After calculating this, now n is greater than or equal to 3.37. In the first step, I got the value of n. N is greater than or equal to 3.37. In the second step, what we have to do? We have to round up that particular value to the next highest integer. So 3.37 means I am rounding that value at n is equal to 4. Now I got the value n is equal to 4. In the third step, what I am going to do? We are finding the transfer function with omega c is equal to 1 radians per second for the value, which value n is equal to 4. And I told you, we got one tabular column, whatever the value we are going to get, we have to consider that particular factors. Now, we got the value n is equal to 4 now, that is, we need to consider these things, that is s square plus 0.7654 s plus 1 into s square plus 1.8477 s plus 1. So, which factor I need to consider? I need to consider the factor which belongs to the value n is equal to 4. Same, we considered that one only. See here, instead of 4, I wrote the factors of that particular value n is equal to 4. I multiplied that, and finally, in the fourth step, we have to find out the value of omega c, and I told that we got the value omega p is equal to, just I considered which formula? First formula, omega pi p divided by 10 to the power of 0.1 ap minus 1 whole to the power of 1 by 2n. Substituted all the specifications and I got the value omega c is equal to 21.3868. Okay. Now, finally we are going to find out the real transfer function of the analog low pass Butterworth filter. For that one, what we have to do? We have to substitute s in the place of s. We have to substitute s tends to omega c, that is equal to s divided by, we got the value omega c is equal to 21.38. Okay. In all the value of s in the third step, we need to substitute that s with s by 21.386. Okay. See here, in the place of s by 21.3, in the place of s, just we substituted it with s by 21.3868. After all calculating, this is the final transfer function what we got, which is nothing but the analog Butterworth transfer function low pass for the low pass filter. So, this is the 5 steps how we are going to design the analog low pass Butterworth filter. This is for one specifications. Now, if you see the second problem, just consider the specifications. Here the specifications are somewhat different. 0.9, 0.2. And if you see here omega 0.2 pi, 0.4 pi, that means we got the value 1 by square root of 1 plus epsilon square is equal to 0.9 and 0.81. After doing that, we got the value 1 by lambda 1 by square root of 1 plus lambda square is equal to 0.2. This is this thing. So after finding the value, we get omega p is equal to 0.2 pi. See here, omega p and omega 4 pi is nothing but omega s. The specifications are somewhat different when we consider it with the first problem. Okay. Now same, steps will be same, but the specifications will be different. So depending upon this specification, we consider which formula. See here, I consider the second formula, n greater than or equal to log into lambda by epsilon by log omega s by omega p. Substituting the values, I got n is equal to 3.3434. So the second step, I rounded that particular n value to the next higher value, that is n is equal to 4. Third step, what we are going to do? What are the factors belonging to that particular value n is equal to 4? That I have taken here. That is omega c divided by capital N is equal to 4. That is equal to 1 divided by, this is the factors which is related to the value n is equal to 4. Just we have saw that in the tabular column for the value of n factor n is equal to 4, the factors are s square plus 0.76 s plus 1 into s square plus 1.84 s plus 1. These are the factors which is related to the value n is equal to 4. Now, the fourth step, we are going to find out the value of omega c. Omega c is equal to 0.24 pi. And what we are going to do in this fifth one, just we are substituting in the place of s by omega c, that is equal to s divided by, you know the value of omega c, that we are substituted in all the place of s. In the place of s, just we have substituted this particular value. Okay. Just after doing all the calculation, this is the finalized transfer function of, let it be HA of s, sorry. So this is the finalized transfer function of the analog low pass Butterworth filter. Okay, so the first step we have completed. From here, what we are going to do? Here we are going to convert that particular analog filter into the digital filter by using the two techniques, which is nothing but the impulse invariant method and bilinear transformation, which we'll see that in the upcoming classes. Okay, so this is all about the designing of the analog low pass Butterworth filter for getting the transfer function of the analog filter. Okay, so this is one of the technique. In the next class we will see the another technique, which is nothing but the Chebyshev filter, same but with some different steps, how the analog filter will be created with the help of the Chebyshev filter. Okay, hope you have understand this particular topic. We'll see in the next class, which is related to the Chebyshev filter. Okay, thank you.